please introduce yourself, tell everybody what you do.
Yeah, hi, my name is Flint, and I'm an archaeologist. I've done archaeology my whole life. My dad was an archaeologist, and I'm just very passionate about sharing archaeology and what we do. I find in general that people don't really understand what modern archaeology is about.
They built the pyramids 4,500 years ago, and we just discovered something that should be absolutely impossible. A single microscope image, one mineral, found inside a granite block older than written history.
First of all, thank you for joining me here.
Oh yeah, thank you for having me.
It's in a way a historic occasion, because as far as I know, this is the first time ever that a mainstream archaeologist has sat down in a public forum.
And it has just shattered everything mainstream archaeology has been telling us for over 100 years. Scientists are speechless, engineers cannot explain it, and the academics who spent decades calling this man a fraud. They have gone very, very quiet. This discovery does not just change how the pyramids were built, it changes how advanced ancient civilizations actually were. And nobody was supposed to find this. Most people, when they think about the mysteries of ancient Egypt, picture the pyramids themselves, their sheer size, the logistics of moving millions of stone blocks, the astronomical precision of their alignment. These are fair questions, and over the decades, researchers have developed reasonably convincing answers. The majority of the pyramid structures are limestone, a relatively soft and workable material. With enough labor, enough organization, and enough time, limestone can be shaped and moved in ways that, while extraordinary, are at least explainable within the boundaries of what we know about ancient tools and human effort. But limestone is not the real problem. The real problem is granite. Granite is a completely different material. It is composed of quartz, feldspar, and mica, and it rates between 6 and 7 on the Mohs hardness scale, which is the standard measure used to rank the scratch resistance of minerals. For context, a copper nail rates around 2.5 to 3 on that same scale. Granite is not just harder than copper. It is so much harder that in practical terms, trying to cut granite with a copper tool is a bit like trying to scratch glass with a piece of chalk. The softer material simply cannot impose itself on the harder one in any meaningful way. Yet the ancient Egyptians did not just cut granite, they cut it with a level of precision that continues to puzzle engineers and material scientists today. The King's Chamber, located at the heart of the Great Pyramid of Giza, is built entirely from granite blocks. Some of those blocks weigh over 70 tons. The Valley Temple at Giza contains massive granite elements where the joints between individual pieces are so tight that a razor blade cannot be slid between them. Statues carved from single granite blocks show surface details that appear, to modern eyes, almost machined. And then there are the drill cores. At various ancient Egyptian sites, researchers have recovered cylindrical cores of granite that were clearly produced by some kind of rotary drilling process. These cores show something that has genuinely unsettled engineers who have examined them. The spiral grooves left by the drilling tool descend into the stone at feed rates, meaning the rate at which the drill advances into the material, that is, by any modern standard, extraordinary. Chris Dunn, a manufacturing engineer with over 4 decades of experience in precision machining, examined these ancient artifacts firsthand. His assessment was unambiguous. The tolerances he was observing, surfaces flat to within 1/1000th of an inch across distances of several meters, drill holes maintaining perfect circularity throughout their entire depth, were not just impressive examples of ancient craftsmanship. In his professional judgment, they were industrial. He stated that what the ancient Egyptians achieved in granite matched or exceeded the standards produced by modern CNC machinery. Not approximately, not loosely. Precisely. This is not a fringe opinion from someone with no relevant experience. Dunn spent his career surrounded by precision manufacturing. His reading of the evidence carries weight. So what has the mainstream academic explanation been? For well over a century, the accepted answer has rested on 2 primary methods. The first is copper saws, used with sand as an abrasive. The second is the use of dolerite pounders, heavy balls of a hard volcanic rock that workers would use to bash and grind away at granite surfaces through sheer repeated impact. Both methods are real. Both methods leave traces in the archaeological record. Neither method, according to the evidence, is sufficient to explain what we are actually looking at. The copper and sand theory faces a fundamental materials problem. Sand, which is largely composed of quartz, does have some abrasive capacity against granite, but copper itself, rating around 2.5 on the Mohs scale, is far softer than the granite it is supposedly cutting. When you attempt to cut a harder material with a softer one, even when using an abrasive slurry, the tool wears down at a rate that makes the process extremely slow and produces surfaces that are rough and inconsistent. Dennis Stocks, an experimental archaeologist based at the University of Manchester, spent years conducting controlled tests of copper tools with sand on granite. The results were published and are available in the academic record. Progress was measured in fractions of a millimeter per hour. Copper wear was rapid. The resulting cut surfaces were uneven and bore no resemblance to the smooth, precise finishes found on ancient Egyptian granite work. Stocks himself acknowledged that his experiments raised more questions than they answered. Dolerite pounding is similarly limited. It does work. Percussion with a hard, heavy material can gradually remove granite through repeated impact, and there is physical evidence that ancient Egyptians used this technique. But the speed is agonizingly slow. To shape even a modest granite surface through percussion takes hundreds of hours of sustained manual labor. Scale that up to the King's Chamber, which contains an estimated 400 to 500 granite blocks, and the labor hours required for granite work alone climb into the millions. More critically, neither copper sawing with sand nor dolerite pounding comes close to explaining the precision. Surfaces flat to 1/1000th of an inch do not result from rocks and soft metal. Drill holes of perfect circularity do not come from handheld abrasive tools used without any form of mechanical guidance. The physical evidence and the conventional explanation simply do not match. This is the point that Graham Hancock had been making for roughly 4 decades. Hancock is a British journalist and author who has spent much of his career writing about anomalies in the ancient world. His 1995 book Fingerprints of the Gods brought him widespread public attention and an equally widespread dismissal from professional archaeologists, many of whom viewed his work as speculative at best and sensationalist at worst. His lack of formal academic training in archaeology was consistently used to discount his arguments, regardless of the specific evidence he was presenting. But on this particular question, the question of how granite was cut with such precision, Hancock was not offering wild speculation. He was pointing at a genuine gap between the physical evidence and the accepted explanation. Experimental archaeology had failed to replicate ancient results. Engineering analysis of the artifacts consistently produced assessments that the official methods could not account for. And for 40 years, the mainstream response was largely to dismiss the question because of who was asking it. That approach became significantly harder to sustain in 2022, when Hancock connected with a scientist who had no stake in the debate, no reputation to protect in Egyptological circles, and no interest in anything beyond what the physical evidence actually showed. What that scientist found when he put a 4,000-year-old granite surface under a scanning electron microscope is where the story changes entirely. Dr. Masoud Garb is a material scientist whose professional work sits within a field called tribology. It is a discipline that most people have never heard of, but one that underpins a significant portion of modern engineering. Tribology is the study of friction, wear, and lubrication, the science of what happens when surfaces interact under pressure. It is a field built on precision measurement, controlled experimentation, and a very detailed understanding of how materials behave at a microscopic level. It is about as far from ancient history as a scientific discipline can get. That distance, as it turned out, was exactly what made Garb's involvement valuable. In 2022, Hancock approached Garb with a straightforward proposition. Ancient Egyptian granite artifacts existed. Those artifacts showed cut surfaces that the accepted historical methods could not convincingly explain. Would Garb be willing to examine those surfaces using the instruments available in a modern tribology research facility and report what he actually found? Garb, by his own account, had no particular position on ancient Egypt. He was not an Egyptologist. He had no professional reputation tied to any existing theory about how the pyramids were built. He was a hard scientist presented with a hard problem, and he agreed to take a look. The two obtained the necessary permissions to examine ancient Egyptian granite artifacts using scanning electron microscopy combined with energy dispersive X-ray spectroscopy. These are not ordinary laboratory tools. A standard optical microscope, even a powerful one, has limits imposed by the wavelength of visible light. Scanning electron microscopy operates on a completely different principle, using focused beams of electrons rather than light, and can resolve surface features at a scale measured in nanometers. Energy dispersive X-ray spectroscopy adds a chemical dimension to that imaging capability, allowing researchers to identify the elemental composition of material embedded within a surface at a molecular level. Together, these instruments allow a scientist to look at an ancient cut surface and determine with a high degree of confidence exactly what is in it and what the wear patterns look like at a level of detail that no previous examination of these artifacts had been able to achieve. Garb began the examination with a clear expectation of what he would find. The accepted story, repeated in Egyptology textbooks and academic papers for over a century, held that ancient Egyptian granite cutting was accomplished through abrasion using sand, combined with copper tools. If that story was correct, the surfaces should show a chemical and physical fingerprint consistent with that process. Sand particles, copper residue, wear patterns characteristic of a relatively soft abrasive being dragged across a hard surface. These are all things that scanning electron microscopy and X-ray spectroscopy would identify with no ambiguity whatsoever. That is not what the instruments showed. The wear patterns on the ancient cut surfaces were inconsistent with sand, abrasion. The scratch signatures, the microscopic marks left by the abrasive material as it moved across the granite, did not match the profile that quartz-based sand produces. Something else had been in contact with those surfaces. And when Garb used the X-ray spectroscopy to isolate and identify the material embedded within the ancient cutting grooves, he found corundum. Corundum is aluminium oxide. It is one of the hardest naturally occurring minerals on Earth, rating 9 on the Mohs hardness scale. To put that in context, diamond sits at 10. Corundum sits at 9. Granite, the material being cut, rates between 6 and 7. The difference between a 9 and a 6 or 7 on the Mohs scale is not a small step. The scale is logarithmic in nature, meaning that the gaps between numbers represent significant differences in actual hardness. Corundum is dramatically harder than granite. It is the mineral that forms rubies and sapphires, and in its synthetic form, it is one of the most widely used industrial abrasives in modern manufacturing precisely because of its capacity to cut through hard materials efficiently and cleanly. Garb himself noted that the reason aluminium oxide is so commonly used in modern industry, and the reason the warranties on products that incorporate it tend to be strong, is directly related to the fact that it sits just below diamond on the hardness scale. There is almost nothing it cannot cut effectively. Finding corundum embedded in a 4,000-year-old granite cutting groove was not an expected result. It was not a result that fit anywhere within the conventional framework of ancient Egyptian technology. Corundum does not occur naturally in Egypt in any form that would make it readily available for use as an industrial abrasive. The nearest significant natural sources lie in regions that ancient Egypt had documented trade connections with, but the critical point is not just the availability of the mineral. The critical point is what using it effectively actually requires. Garb was clear on this. Using corundum as a cutting abrasive is not something that happens by accident. You cannot stumble across some corundum, rub it on a rock, and end up with a surface flat to 1/1000th of an inch. To use it effectively, you need to understand mineral hardness at a level that goes well beyond everyday observation. You need to grind the corundum down to specific particle sizes, because particle size directly affects both cutting speed and surface finish. You need to mix it into a slurry at a precise consistency, because the ratio of abrasive to liquid determines how the material behaves in a cutting groove. Too thin, and it loses its cutting power. Too thick, and it clogs the groove and stops working. Every variable in the process needs to be understood and managed. Garb described what he was looking at not as lucky improvisation or accidental discovery, but as material science, deliberate, systematic, and sophisticated. The implications of that finding were significant enough that Hancock decided replication was the necessary next step. A single microscope result, however compelling, is evidence. It is not proof. Proof requires the hypothesis to be tested, challenged, and shown to produce consistent and predictable results under controlled conditions. In early 2023, Hancock organized a series of experimental trials designed to do exactly that. The setup was straightforward: a workshop, granite blocks, copper tools. 3 different abrasive materials tested independently under conditions as controlled as a practical workshop environment allows. The team included both stonemasons with extensive hands-on granite experience and material scientists who could monitor and measure what was happening throughout the process. The 3 abrasives tested were sand, representing the conventional theory, quartz powder, which is harder than ordinary sand and was available in ancient Egypt, and a corundum and quartz, slurry, representing the new hypothesis. The results were not subtle. With copper tools and sand, the cutting rate came in at roughly 0.5 millimeter per hour. Copperware was heavy. The resulting surfaces were rough and inconsistent, matching what Dennis Stocks had found in his earlier experiments at Manchester. With quartz powder, the rate improved slightly to around 0.8 millimeters per hour. Still far too slow to account for the scale of ancient Egyptian granite work, and still producing surfaces that bore no meaningful resemblance to ancient finishes. Then they switched to the corundum and quartz slurry. The cutting rate jumped to over 3 millimeters per hour, more than 6 times faster than sand. Copper tool wear dropped dramatically. The cuts produced were smooth, clean, and geometrically accurate in a way that neither of the other abrasives had come close to achieving. But it was the drilling component of the experiments that produced what several participants described as the most striking result of the entire series. When the corundum slurry was used in the drilling tests, the resulting core samples showed spiral grooves descending into the granite. Those grooves matched, in their pattern and dimensions, the spiral grooves found in ancient Egyptian drill cores, the same grooves that had been puzzling engineers for decades. The same grooves that no previous experimental attempt using copper and sand had ever been able to reproduce. They were right there on the workshop table, cut fresh into modern granite using ancient methods, looking identical to artifacts that had been pulled from sites along the Nile thousands of years earlier. Nick Geezer, a stonemason with decades of hands-on granite experience who participated in the trials, described what it felt like when the corundum slurry was introduced. He said the copper stopped fighting the stone and started guiding the abrasive. The resistance dropped, the cut went smooth, the speed increased noticeably as tools wear fell away. He said it was the first time in his entire career that he could genuinely see, in a practical and physical sense, how the ancient Egyptians had actually done it. What the experiments also revealed, however, was that working with corundum slurry was not a simple process that any unskilled worker could pick up and apply. The technique demanded real expertise. The mixture consistency had to be maintained within a fairly narrow range throughout the cutting process. Pressure on the tool had to be applied evenly. Temperature in the cutting groove needed to be managed. Any significant deviation in any of these variables affected the quality and speed of the cut. The process, in other words, required craftsmen who understood their materials deeply, who had built up that understanding through sustained practice, and who were passing that knowledge down through structured training from one generation to the next. That kind of specialized multi-generational craft knowledge is entirely consistent with what we know about how the ancient Egyptians organized skilled labor for major construction projects. By the time the experimental trials were complete, 3 independent lines of evidence were pointing in the same direction. The microscopic analysis had found corundum where the conventional theory said there should be nothing but sand and copper residue. The experimental replication had demonstrated that corundum-based slurry produced results matching ancient artifacts in both speed and precision, while sand and copper alone consistently failed to do so. And the material science data provided a coherent explanation for why the process worked, grounded in the known properties of the minerals involved. It was, by any reasonable scientific standard, a hypothesis worth taking seriously. What happened when it reached the broader academic world is a different story altogether. Hancock chose not to present his findings at an archaeology conference. That decision was deliberate, and in hindsight, it was probably the right one. Instead, in late 2023, he brought the corundum research to a material science conference, a room populated by engineers, physicists, and material scientists whose professional training is built around evaluating physical evidence on its own terms. The reception was largely positive. The methodology was scrutinized, as it should be in any serious scientific setting, and the data was engaged with directly. Researchers in that room were equipped to assess scanning electron microscopy results and experimental cutting trials, because those are the kinds of tools and methods they work with themselves. The findings were not dismissed, they were discussed. Dr. James Harold, a geological archaeologist who has spent decades studying ancient Egyptian quarrying techniques, offered a particularly relevant observation during the period following the conference. He noted that abrasive slurries, by their very nature, do not tend to preserve in the archaeological record. A liquid mixture applied to a cutting groove during the construction of a structure 4,000 years ago is not the kind of material that survives intact through millennia of exposure, burial, and the passage of time. Physical tools can survive, stone structures obviously survive, but the consumable materials used in a cutting process, the slurry itself, the liquid carrier, the abrasive particles in suspension, are almost always gone. Harold's point was that corundum traces embedded within the cut surfaces of ancient granite artifacts might represent the best physical evidence we are ever likely to recover of the actual abrasive technology the Egyptians used. It is not a gap in the evidence. It is what preservation under these conditions realistically looks like. That context matters because one of the questions raised in response to the findings was entirely reasonable. If corundum was being used systematically in ancient Egyptian stoneworking, why has it not shown up before in the archaeological record? The answer, as Harold's observation suggests, is that the question itself may be based on a misunderstanding of what we should expect to find and where. Nobody had previously looked for corundum in ancient cut surfaces using scanning electron microscopy and X-ray spectroscopy because nobody had thought to look there. The conventional story was so firmly established that it had effectively closed off that line of inquiry before it started. When the findings moved beyond the material science community and reached mainstream Egyptology, the response was more complicated. It did not arrive as a single, unified reaction. Some archaeologists engaged with the substance of the research. They asked questions that any good scientist should ask. How much corundum would have been required to work granite at the scale the ancient Egyptians were operating? Is there documentary or physical evidence of corundum trade during the dynasties, responsible for the major granite structures? Could the traces identified by Garb represent later contamination rather than original cutting material? These are legitimate questions. They are the kind of questions that move a hypothesis forward by identifying what additional evidence is needed to strengthen or challenge it. Science is supposed to work this way, and the archaeologists who engaged on those terms were doing their jobs properly. But a significant portion of the academic establishment responded differently. Rather than engaging with the data, they engaged with the name attached to it. Graham Hancock, the outsider, the journalist, the man who had spent 40 years writing books that challenged mainstream interpretations of ancient history and had been consistently dismissed, mocked at conferences, criticized in journals, and described in fairly blunt terms by various academics as someone whose work did not meet the standards required for serious consideration. For many, within that establishment, his name had become a kind of automatic disqualifier. The position, stated with very little apparent discomfort, was that Hancock's involvement tainted the findings regardless of their scientific merit. The data produced by Dr. Garb's laboratory analysis did not matter. The experimental replication carried out with stonemasons and material scientists did not matter. The peer review that the findings had received from credentialed scientists with no stake in the outcome did not matter. The name on the paper was enough. Hancock spoke about this in a 2024 interview. He described being told by Egyptologists that even if the corundum finding was correct, he should not be the one presenting it. That his lack of formal academic training in archaeology disqualified him from contributing to the conversation, even when he was working alongside and presenting the results of scientists who had all the credentials his critics demanded. His interpretation of that response was straightforward. It was not, he said, about the truth. It was about who holds the authority to rewrite the accepted story of human civilization, and about protecting that authority from people who do not belong to the institutions that currently hold it. That is a serious charge, and it is worth being clear about what it does and does not imply. Academic gatekeeping is a real phenomenon. The sociology of how new ideas get accepted or rejected within established disciplines has been studied extensively, and the pattern of outsider challenges being dismissed on the basis of the challenger's credentials rather than the quality of their evidence is well documented. At the same time, the credentialing system exists for reasons that are not simply self-serving. Expertise matters. Methodological rigor matters. The history of fringe theories about ancient Egypt is long and includes a great deal of work that deserves the skepticism it receives. The problem is not that standards exist. The problem is when those standards are applied selectively, used as a tool to avoid engaging with inconvenient evidence rather than to evaluate it fairly. What is notable about the corundum research is precisely that it was designed to be difficult to dismiss on methodological grounds. Garb is a credentialed material scientist working in an accredited research institution. The analytical instruments used are standard in the field. The experimental trials were structured with a control methodology and produced quantifiable, reproducible results. The findings were presented at a scientific conference and subjected to scrutiny from peers in relevant disciplines. If the same research had arrived under a different name from someone whose career sat entirely within the mainstream of Egyptological study, it is at least worth asking whether the reception would have looked different. The corundum hypothesis has continued to gain traction in the period since the initial findings were published. Not universally and not without ongoing debate, but the engagement it has found among engineers, material scientists, and a growing number of archaeologists willing to assess the data independently of its origin suggests that it is not going to be quietly set aside. The evidence is not disappearing. The experimental results are replicable by anyone with access to a workshop and the right materials. The microscopic findings are documented and available for independent verification. It is also important to be precise about what the corundum discovery does and does not establish. Hancock has, over the course of his career, proposed a range of ideas about the ancient world, some of which remain highly contested and are not supported by the weight of available evidence. The corundum finding does not validate all of those ideas. It addresses a specific and well-defined question, which is how the ancient Egyptians cut granite with the level of precision that modern engineers consistently find remarkable, and on that specific question, the evidence makes a compelling case. If the ancient Egyptians were deliberately sourcing corundum, processing it into abrasive material of a specific particle size, and incorporating it into cutting slurries used for granite work, the implications for how we understand their technological capabilities are substantial. It means they understood mineral hardness in a way that goes well beyond the basic empirical knowledge that any stoneworking culture would accumulate over time. It means they were maintaining long-distance trade networks for the specific purpose of sourcing industrial materials that were not available in the Nile Valley. And it means they had developed processing techniques, grinding a mineral to optimal particle sizes, formulating slurry mixtures to consistent ratios, managing the variables of a precision cutting process across large workforces that constitute genuine material science in any meaningful sense of that term. None of that makes them mysterious or supernatural. It makes them capable. It makes them people who understood their materials, organized their labor effectively, and solved difficult engineering problems through accumulated knowledge and systematic refinement of technique. The picture that emerges is not of a primitive civilization doing something it should not have been able to do. It is of a sophisticated civilization being more sophisticated than we had previously given it credit for. There is a broader question sitting underneath all of this, and it is one that researchers in a number of fields have begun to take more seriously in recent years. If a technology as significant as corundum-based abrasive slurry was hiding in plain sight on surfaces that thousands of researchers had examined over more than a century, visible only because someone thought to use the right instruments and ask the right question, then the obvious follow-up is what else might be similarly hidden. How many other ancient techniques have been dismissed as impossible or explained away with inadequate theories because the tools or the curiosity needed to look properly were never brought to bear? The ancient world is not as well understood as the confidence of some academic writing about it might suggest. The corundum finding is a reminder of that, and a reasonably striking one. In a tribology laboratory, a scientist with no prior involvement in Egyptology placed a 4,000-year-old piece of granite under a scanning electron microscope and found a mineral that, by the logic of the accepted story, had no business being there. In a workshop, an experienced stonemason loaded a copper blade with a corundum slurry and watched it move through granite the way ancient tools must have moved when the structures along the Nile were still being built. The gap between what the conventional explanation predicted and what the physical evidence actually showed turned out to be large, enough to matter. The question of how the ancient Egyptians cut granite with such extraordinary precision has not been completely and finally answered. Science rarely works that way. But the question is now in a different place than it was before 2022, supported by physical evidence, experimental replication, and material science analysis that collectively point toward an answer more interesting and more flattering to the people who built those structures than the one that had been repeated for 100 years.